All right, my friends, sorry about this, but I thought I was done, but then I looked at my notes and I realized there's just a little bit left to talk about that goes with 3.3 Part 1. Part 1 is a bit of a beast. Anyway, as far as going over it, so basically we need to talk about what's called derivatives of higher order. Okay, so let's talk about that in terms of notation. So we'll talk about how do you handle it using function notation versus Leibniz notation. Okay, and I hope you are starting to feel like you're getting a little used to Leibniz notation as we go. Okay, so for function notation, let's say, we'll just do this using an example. Let's say I give you f of x equals 2x to the fifth minus 3x squared. Well, if we take the derivative with respect to x of both sides, then what's the notation we would use for the derivative of f of x? We would call it f prime of x. And then what would the derivative be? So the derivative of 2x to the fifth is 10x to the fourth. The derivative of 3x squared would be 6x. So it turns out, since a derivative is a rate of, and it's basically an instantaneous rate of change, so for example, let's say your original function is like a position function, then the first derivative would be a velocity function. Well, what if you want to know what the rate of change is of that rate of change for some reason? So maybe you want acceleration. Well, you would need to take the derivative again. So the derivative of the first derivative is called the second derivative. And the first derivative, as I'm pointing to here, has a nickname f prime, and then the second derivative has a nickname f double prime. So if you write f double prime of x, all it means is that you took the derivative of the first derivative. So you would get 40x cubed minus 6 for this example, for the second derivative of f. And what if, for some reason, you feel like you need to take the derivative of the second derivative? Well, you would get the third derivative, and its nickname would be f triple prime. And you would simply, in this case, get 120x squared. Now, I hope it makes sense that this prime notation is going to run into issues, since you can, theoretically, there's no limit to the number of derivatives that you can take. So, you don't want to be having something like this, f, that type of notation just wouldn't work. So, after 3, instead of using the prime notation, you'll see a change in notation. So right after the third derivative, they'll switch to the number of derivatives in parentheses. So this would mean the fourth derivative of x. The fourth derivative of f with respect to x. And it just simply means that you would take the derivative here of the third derivative. So you would get 240x. Okay, and then after, like I said, beyond 4 and beyond, we would use this notation where the number of derivatives is in parentheses and superscript. And notice, once we get to 0, if somebody wants to know what's the 7th derivative, 8th derivative, and so on, from here on out, the answers would all be zeros. So I'll just go ahead and say, and so on. Okay? All right, so really what I'm trying to do here is just make sure that you know what is meant by first or second derivative, and then also how easy it is and how to handle the notation, whether you're in function notation or Leibniz notation. Okay, so let's tackle the same thing but using Leibniz notation, and I'll just use a slightly different example. So, or maybe not. Anyway, let's say we do, this time it would be y equals. Remember, if your work is prompted with f of x, then you would use function notation. If your function rule is prompted with y equals, then you'll practice Leibniz notation. So let's say we have, I don't know, x to the sixth minus 5x to the, should I do 10? 10's horrible. Okay. So notation here, we've already talked about if you take d dx of y, the notation for that is dy dx. So f prime dy dx, saying the same thing, just two different ways of saying it. So in this case, we'd get 6x to the fifth minus 15x squared. Okay, now let's talk about what if you need to take the derivative of dy dx. What is the notation? So a note here. If you take d dx of dy dx, the notation looks like multiplication. So it would be d squared y over, and then dx is actually considered one character as opposed to a d and an x because it just means change in x. So you'll just see dx squared with no parentheses because this was considered just one character by Mr. Leibniz. So what that means is that this is the notation for the second derivative in Leibniz notation. So if we're using this example for d squared y over dx squared, you'd get 30x to the fourth minus 30x. Similarly, as you continue, if you do d dx of the second derivative, again, kind of look at it like multiplication, you'd get d cubed y over dx cubed. So this is the notation for the third derivative. So the third derivative would be 120x cubed minus 30. And then it just follows from there. So, and there's no notation change with Leibniz. And so on. And you could continue like that forever if you want. All right, my friends, I hope this helps. In your first worksheet, you'll be asked just to do the first and the second derivative using Leibniz notation. So hopefully this will help you to know how to write your answers. Take care, everybody.